So, but anyway, also I know it's quite late in the afternoon, and let's see how long gonna take me to get you guys into sleep. See, my name is Ray. I'm a research faculty in the biostatistics department here in University of Rochester. Today I'm going to talk about some statistical methods in bioinformatics. So bioinformatics is a quite broad concept. So in fact, today I'm going to focus on the so-called gene expression data. So hopefully at the end of this talk, you guys will get a roughly idea. In the future, maybe you will get your own, gene expression data. At that time, maybe you can think about my talk. It may provide some, statistical methods available for you to dig into the data to answer some questions. Okay, so first is to generate the gene expression data. There are many ways. The most popular way in the past 10 years is the so-called microarray technology. Like in last century, in late 90s, people start to use this technology to measure gene expression data. There are different platforms, as you can see here, Affymetrix, Illumina, but it doesn't matter. Eventually, they will provide you with the gene expression data. And in recent years, the so-called next generation sequencing technology, it's a pretty new technology. It provides better measurement in terms of the testing power. Downstream testing power is better, and this technology is quite new. So in this talk, I will still focus on the microarray part, but doesn't matter. Later on, if you happen to have the RNA-seq data, next generation sequencing data, you still can apply similar, maybe do a little bit adjustment, still apply to your data. So before I get into the real data, I have to talk about a little bit about how to clean the data first. So micro data, we have to do a lot of pre-processing. So as you may already know or not, the microarray actually is from the imaging data. So the first step people would do is do the background correction. So for the imaging data, some part is lighter, some part is darker. So people use some techniques to adjust them so that they remove this layer of noise. Okay, the second step is quality control. Of course, you may have some, bad samples you hope to remove. So people use this procedure to guard against the bad samples. So later on, all your samples are the true sample you can trust on. And third step is the so-called normalization. There are different procedures like quantile normalization, global normalization. The purpose of this is they try to remove the technical noise. So in general, like if you try to measure different people, if I draw some blood from me, draw another blood from you, and run the microarray technology, to make them comparable, you have to try to get rid of this, noise. Maybe for your measurement is a little bit higher. For me, it's lower. So people use normalization procedure to make them comparable. The fourth one is they do the summarization, but for the microarray technology, people use the so-called arrays, the probe sets, to collect the data. So different probes corresponding to multiple probe sets may correspond to a single gene. So because eventually we are more interested in the gene expression, so multiple probe sets, we hope to combine them, summarize them, so that we have a single gene expression. So just like maybe Hu may also talk about log transformation is also popular to make the data more look like normal, so that it's easier for for the downstream analysis. So I know it's not fun to read this, but it doesn't matter. Later on, so you will see. Let's start from here. So what does the microarray gene expression data look like? It's essentially a matrix with m rows and n columns. The rows means genes. Columns means samples or arrays or slides. So basically, the genes are supposed to have a big numbers. Like from the Human Genome Project, it's already known for human genomes there are around 30,000 genes. So you can imagine for this matrix it's quite long. You have a lot of rows, but for the columns it's quite slim. You only have a limited number of slims, arrays or columns. The reason is, first of all, it's quite costly to get the samples. You may only have a couple of samples. And the second is it's hard to get samples. For example, for certain disease, it's hard to recruit patients. So for different reasons, this is how the gene expression data look like. You have the very long, matrix. You have multiple, lot of rows, and also you have very limited sample size columns. So usually the rows range from 10 to 50,000, and also the sample size range from 10 to 100 sample size. In my past experience, I have ever done like for 3 or 4 samples for this kind of microarray. Like in the past few years, even there is one collaborator. He came to me say, "Okay, I only have 1 sample." Okay, I say if you only have 1 sample, it's hard because you don't have replicates. If you don't have replicates, it's hard to do the statistical analysis. So, but anyway, now it's much less inexpensive. So, which is good. Maybe in the future, like if you go to the hospital, the doctor gonna draw some blood from you and do the blood test. Maybe this kind of microarray, gene expression data gonna become the standard, a test. So if a patient go to the hospital, maybe the doctors also wanna measure all your gene expressions to see what happened. Okay, what we can do with the gene expression data? So, what we can do with the gene expression data? So, some straightforward, some simple example is you have thousands of genes. For normal people, you have these thousands of genes, and for the diseased, for example, cancer people, you also have thousands of genes. One typical question is which genes are responsible for the disease? If you can compare them, and then eventually you get a list. This gene list may help you to answer why people get disease, why people get cancer. So I know there are many other ways to diagnose, but at least this gene expression data provide another opportunity, another alternative to diagnose people. This is one example. Okay, throughout my talk, I will use this particular data set. It's leukemia data set. After all the pre-processing, the normalization background checking, we eventually have around 8,000 genes. So 8,000 rows in your matrix. And also we have like 79 samples, 79 columns. In your you can imagine there is a very big matrix there. Okay, so in these 79 samples, essentially there are 2 groups. One is disease, the BCR group, the leukemia group. The other is the normal group. There's no abnormality. So think about, essentially you have 2 matrices. They have the same row, but one have 37 columns, the other have 42 columns. So all the analysis later on I'm going to talk about is focused on this data to see what kind of information we can get from this data, what kind of question we can answer. Okay, here's I just tried to list a couple of typical. Sure.
The previous slide. Lymphoma with the no unsuspected genetic abnormalities, it's a negative control, isn't it? It's not a positive control.
Yes,
Because you said it's normal. Normal.
Yeah, you're right.
They don't show
you're right.
any.
Yeah, because to me, I'm a bad statistician. So for me, it doesn't matter it's normal or not. As long as there are 2. Yeah, you can.
Sounds like a positive control. Then I saw, okay, it is a
okay, thank you. Okay. Anyway, here's the analysis tools we have available, to deal with the data. So some of them, maybe you guys have already.
Just a question. The previous slide, you said there are about 8,000 genes.
Yes.
So depending on the platform that you're using, there are more genes than that. But did you remove some that had very low expression using quality?
I'm not sure how for this particular data set how they did. To maybe they remove some low quality genes, and also maybe they are more focused on this 8,000 genes instead of, sometimes, when you do gene expression experiments, you don't have to measure the whole genome. Sometimes you only need to focus on some. So I'm not sure because I'm not a biologist. I just grab this data, So anyway, so here are all the methods. I believe you guys already know, maybe or may not know some of them. So I will go through them one by one. So the first is a so-called differential gene expression analysis. What does that mean? So as I said, if you have thousands of genes, a typical question would be, like here I introduced some mathematical notations. I know it's not fun to read, but you have around 8,000 genes in one group, NEG group, and also you have another 8,000 genes in the other group. Okay, the typical question would be, for each individual gene, are they the same or not across these two groups? Okay? If they're not, we claim them to be so-called differentially expressed genes. When I say equal or not, I mean their mean are the same or not, or sometimes I mean their distribution are the same or not. So in order to identify these so-called differentially expressed genes, two steps you need to do. The first is the hypothesis testing. Like they use different tests like Ttest, non-parametric test, Wilcoxon test. Okay, you will get around 8,000 p-values, right? Usually what people do is we set up a cutoff, 0.05. Below, for all the p-values below than that, we claim these genes are differentially expressed. But that also introduces a question, how reliable, your list of, your final list, your differentially expressed gene list. So people would also interested in try to guard against the type 1 error to make sure your final list is truly differentially expressed. Okay, I will go through this one by one. The first is the hypothesis testing. So I try to list a few, test methods here. Of course, we have more than that. The first is a very popular one, like this, the two-sample student Ttest. The second is non-parametric test. One popular one is the Wilcoxon rank sum test. So they only make use of the rank. So for the Ttest, you guys already know, you have to make this assumption the data is normal distributed. But for the non-parametric, like the Wilcoxon rank sum test, you don't have to make this assumption. So the last one is a permutation-based test. Like you pull, or this actually is a way to generate the distribution under the non-hypothesis. So for the first two, you know the distribution, so you can, once you calculate your statistic, you can plug into the distribution to see how extreme they are, in your distribution. For the last one, we use the permutation to construct such distribution under the non-hypothesis, which genes do not show any difference. So sometimes also people use the so-called fold change to test. Fold change just means, because remember all the data has been log transformed. The log base is 2. So if you take the difference between, for example, if you have one gene, two conditions, calculate the mean in each condition, take the difference. The difference, actually 2 to this difference, is going to give you the fold change. The fold change is how much they are different. But these fold changes, they do not consider the variance. So if you know if you know the so-called signal to noise ratio, it's very important to consider the randomness, the noise, the variance taken into account. Okay, here is the formula for the student Ttest. As I said on the top, the numerator is the difference of the mean. For each individual gene, you will get a T. I means the genes. I run from 1 to 8,000. So for each individual gene, you will have the mean difference across two conditions. This actually is the top. The bottom, you have the pooled standard deviation. So for each individual gene, you can calculate this T and then plug it into your T distribution to get a p-value. Okay. So the properties for this T statistic, we need some assumptions. We need at least they are normally distributed. And because we know the T-test is quite robust, So even if your data, sometimes your data is not that normal, it's quite okay, according to my experience. But if it's too abnormal, like it's too far away from the normal, you'll be in trouble. So in that case, you may need to consider the non-parametric test. Yeah. Okay. So for the let me go back to the formula of T. Okay, for this T-test, another thing you have to remember is because under the assumption, they are normally distributed, the top and the bottom, statistically speaking, they should be independent to each other. In other words, the mean and the variance should be independent to each other. You should never expect, like if you have larger mean for certain genes, you have also larger or less variance. They should be independent. I mean, once you have some certain number for your mean, your variance should be independent to that. But unfortunately, this is not the case for the microarray data. That's why people introduce this so-called modified T-test. Modified T-test, we call it significant analysis of microarrays. So as you can see, the only difference here is you have S0 on the bottom. The reason they introduce this is, as I said, for the microarray data, if your mean is small, your variance is also going to be small. They are related to each other. If you plot them, you will see a linear relationship, which is bad, because for the T-test, we should not expect this. To get rid of this effect, people try to introduce this S0, so that you can imagine, because this is a quotient, when your mean actually is very small, your variance is going to be small. So when you do the quotient, the variance is going to affect your T-test, T-statistic significantly. So people try to avoid this happen. So they introduce this S0 so that they can stabilize the signal-to-noise ratio. So you don't have to remember the details. For me, I mean, technically, I don't even remember the underneath formula. Whenever I need, I go to check. But this provides, the point is this modified T-test provide another more robust way to do the statistical test for the microarray or gene expression data. Okay. All these are, parametric, and this one is a non-parametric, test. The point is they try to make use of the rank information only. So as you can see, the statistic actually is the summation of all the ranks in one group. So if you combine two groups together for each individual gene and then rank them, for one group you can sum all the rank together. So this is going to be your Wilcoxon, statistic. And then you will get a p-value for this. The point is we only use the rank information. So it's very robust. Why is that? For example, if you have some outlier, very extremely large value, expression value. So for the T-test, because we are calculating their mean, as Homey said, when you try to calculate the mean, this large value has significant impact on your statistics. But when you only consider the rank, no matter how big it is, it's just number one. Okay, that's it. So it's more robust. But another downside is if your data is truly normalized, normally distributed, use this gonna result in low power because you lose information. You only use the rank information to do your test. Okay, here's an example because we have the data, as I said, 8,000 genes, two groups. I set the p-value cutoff as 0.05. I conduct 3 different tests on this data set. The T-test, STEM, and the Wilcoxon rank sum test. So there are around 1,000 genes with p-value less than 0.05. Okay, so here's a number of significant genes. So we can call these genes differentially expressed. But wait a minute. As I said, how confidence we have on this gene list, how much confidence we have. How do we know, they are truly differentially expressed or just by chance? To answer this question, we have to introduce this so-called type 1 error, which means the false positives, which means some gene. Yes? For this, no. Yeah, you are very good point. In practice, you definitely should check if they are normal or not. that's the whole point of the log transformation. Usually, after you do the log transformation, then the data are gonna look quite normal, at least marginally. I'm not sure if you know the relationship between marginal and the joint distribution. The joint is non-normal, but marginally, most of the time they show normal. Yeah.
So for like the preprocessing, there's that normalization process. Does that?
No, that's another story. The normalization means we try to remove the noise.
Right.
Yeah, that's, as I say, different people, they have, their measurements are quite different. So you try to take them together to compare them, make them comparable. So that's the point. So it has nothing to do with this normal. They're both normal, I know, but okay. Okay, here's the results. We have around 1,000 genes, As you can see, the results for these 3 different tests are quite similar. The reason is I have conducted the log transformation, so the data is roughly normal. The results is, I also take a look at the intersection of all these genes. All these, 3 different sets, they are quite overlapped together. So they're quite consistent, in other words, the results. Sometimes, if you are extremely in bad luck, you may have the non-normal data. If that's the case, even if after the normal log transformation, but if that's the case, of course, non-parametric tests like the Wilcoxon test will be better to conduct. For me, in my practice, I always do both to see if they are consistent. And if Wilcoxon test give me, less number of genes, differentially expressed genes, I will use that because I'm more confident. Because the Wilcoxon test, they don't throw in, assumptions on it. They only use the rank. So, but sometimes, when you do this kind of test, maybe Wilcoxon test will only give you only a few genes. So my biology, collaborators, they will feel, okay, it's not in my expectations. They are more happy with, more genes. So if that's the case, I will, of course, test the normality and also use the Ttest.
So how many genes are common in all these 2 groups?
Around more than 900. Yeah, I didn't list it here, but yeah, it's more than 900.
More than 1,000.
1,000.
900. No, 900. Close, yeah, close. But yeah, you always have, because they are in different scenarios, so you always have some, mismatch. Okay, so to answer the question, how reliable these gene lists are, I have to introduce this standard table. Like you have true non-differentially expressed genes and the true differentially expressed genes. And also you use your test, you may or may not get your conclusion right. So as you can see on the diagonal, non-differentially expressed is claimed as non-differentially expressed, so you're right. So on the diagonal it's right, but on the anti-diagonal you get errors. So in microarray experiments, people are more interested in these false positives, because I'm not sure how you guys understand the magic number 0.05, how you understand that. The 0.05 actually means, say, if you do 100 tests, even if your test actually underneath they are essentially the same, there is no difference at all. You always expect 5, false positives. But you can imagine in the gene expression data analysis, you have how many genes, like thousands of genes, multiply like 8,000 here. If you multiply 0.5, it's going to give you around 400. 400 is quite a large number. As you can see, I have around 1,000 differentially expressed genes, but inside you have 400. It's a disaster. So people try to figure out some ways to reduce these false positives. So I will talk about a few ways to do that. So again, let's focus on the false positive, how to control it. To control it, we have to define different so-called error rates. The first is a so-called family-wise error rate, FWER. It's defined as a probability of there is at least one false positives. So this is only a probability, as you can say. If eventually, after you conduct all the tests, at the end of the day, you get this probability controlled, under the significance level, for example, 0.05, you are pretty much sure all your finalists are truly differentially expressed, because the chance there is at least one false positive is only 0.05. So it's very small. Okay, so one way to guard against the family-wise error rate is the so-called Bonferroni procedure. It's quite simple and straightforward. What you need to do is you only need to multiply the number of tests. For example, we have 8,000 genes. After you get your p-values, 8,000 p-values, what you need to do is you need to multiply 8,000 to this, all your raw p-values. And then you will end up with a new so-called adjusted p-value, the second row, the adjusted p-value. Of course, this p-value cannot go beyond 1, so we cut at 1. But anyway, you will get a so-called adjusted p-value. And then you apply your threshold 0.05. So if this value, the adjusted p-values are smaller than 0.05, now you are more confident. You know you get your FWER control. You know the chance to have at least one false positive is only 0.05. It's almost negligible. So the last row is only one example, how to calculate. Like if you have the raw p-value 0.04, it's significant before you do the adjustment. But after you multiply the 20, it's 0.8, it's not significant anymore. So the purpose of this procedure is they focus very hard on the low end, the extremely small p-values. Like Home also talk about the multiple testing. Like when you do an ANOVA, the point why people want to do ANOVA first, because if you want to do pair comparison, you will have a lot of pairs. When you have a lot of pairs, you have to consider this multiple testing problem. In other words, multiply your tests by the number of m, for example. That is going to result in low power. So statisticians, they invent ANOVA so that you can only look, if they're different. You don't care which groups they are different. You just look at, across all groups if they are different. If they are and okay, then you can go ahead to say, which group they are different. So that's the whole purpose of the ANOVA. Okay, so the FWER, as you can see, you multiply 8,000 to each individual raw p-value. Of course, it's very conservative. So people try to invent some, not that conservative procedures, also control the FWER. The idea actually is for the Bonferroni, you multiply 8,000. But sometimes it's not necessary. For some p-values, it's not necessary to multiply 8,000. The reason is if it's extremely small, you should penalize more. But if the p-value is not that small, you should adjust your penalize. You should penalize less. So for the Bonferroni, everybody penalize the same, multiply 8,000, which is, of course, it's good, but it's very conservative. So if we want to relax it a little bit, technically, we can use this kind of procedures to penalize the p-values differently, so that you will get a little bit more power. But trust me, it's only a little bit more, not very much. Okay, another thing is that genes actually are correlated to each other. They are highly correlated to each other. So all the procedures I talked about previously, they basically consider genes independently. They assume the genes are independent with each other. The reason they need this is the statistical test has to be independent to each other, so that, for example, they can multiply the number of tests. But this is not the case in the microarray gene expression data analysis. So people like Westphal and Young, they develop this procedure so that they permute the data set so that they will keep the gene dependent structure. So you don't have to worry about details, but the point is here is less conservative. It's more powerful. But the problem for this procedure is because it's permutation, so it's very time consuming. For the Bonferroni, for example, you can do that in 1 second. But for this, it takes a while. So it depends on how much time you have and how much you worry about the type 1 error and the power. You can choose from these different procedures. Okay, here's the results for the previous data. We have around 1,000 non-adjustment, differentially expressed genes. But with Bonferroni, the number reduced to only like 30. So it's very small. But the good thing is for this around 30 genes, we are very confident. We know they are truly different. So we are very confident. But for this 1,000, at least you will say at least 400 is junk. So
further downstream analysis, I think this is very, very much useful. Because more reliable and then it will resolve significant ones.
Yeah, it's more reliable. Later on, I will talk about other analysis. It's gonna be based on this 20, 30, because it's very reliable. I trust them. They're truly differentially expressed. Okay, as I said, the FWER is quite conservative. So statisticians, they try to invent some less conservative procedures. So the FDR, false discovery rate, is one choice. As I said, for the FWER, it's very conservative because the chance you make one type of error, one false positive, the chance is only 0.05. But sometimes my collaborator would say, okay, in my final gene list, maybe I will allow certain number of false positives. For example, if you have 100 genes, maybe I can allow 5% is false positive. I'm okay, as long as I get majority correct, I'm fine. So statisticians, they invent this so-called false discovery rate controlling procedure. As you say, it's a quotient, it's a proportion of your false positives over all your positives. Say if you have 100 genes to be differentially expressed, among them, if you get this FDR controlled, among them, on average, you will have around 5 false positives. Of course, you don't know which 5, but you know the proportion of the mistakes you have. Okay, so this is a most common way to control the FDR, the Benjamini-Hochberg procedure. So as I said, 0.05, you have 5% in your final list, as the false positives. Okay, so first, of course, the advantage is less conservative, it's more powerful. You will get more genes showing, differentially expressed. But there is some disadvantages. One is you allow certain junks into your final gene list. But another one, actually, I don't think many people realize this. Another one is because this FDR is a quotient. The quotient is always not stable. And for this, it's even an expectation, it's an average of the quotient. So it's not very stable. Not very stable, what does it mean? It means, for example, here we have 8,000 genes. We apply this procedure, we will get a gene list, but we only did once, right? One experiment. Inside we have 8,000 genes. Okay, for example, if you have another couple of 8,000, you do the same. This FDR basically control, on average, your final false positives is only 5%. But for your particular one, you don't know. So you can only say, okay, on average, you have 5%, for example, if your level is 0.05. But it's only an average. Average maybe have bias, may or may not is truly 5%. So I have done a lot of simulations here, and we found the results fluctuate a lot. So if I were you later on, when you do your analysis, the first choice, of course, would be the FWER. And if the end you do not have any choice, if there is no power at all, you can try FDR, of course. People understand that, but you have to keep this in mind. It's not very stable, and you do have junks into your final gene list. Okay, here's the results. As you can see, there is 200 around. So 200 is quite okay number, for the downstream analysis. But for the 30 or 20, it's not that. Depends on what kind of question you want to, answer. Okay, these are all about the so-called differentially gene expression analysis. We focus on the mean difference of each gene to see if they have any difference across normal or abnormal groups. The next analysis tool I'm going to cover is so-called differential gene coexpression or differential gene association analysis. What does this mean? It's pretty similar to the previous one, but the difference here is the previous one we focus on the mean difference of genes across two different groups, but here we focus on the relationship of a particular gene with all other genes. We don't care if their mean change or not. We are interested in their relationship. Particular gene, its relationship with others change or not. One example actually would be like in HIV. People knows the response, immune response system get destroyed. How it works? You can, for me, like a statistician, I understand this way. When you get a cold, the HIV virus didn't kill you. Maybe the flu virus kill you. The reason actually is when you get HIV, for the normal people, if you do not have HIV, when you get flu, you will cure it. Your body gonna respond and generate something to kill the virus. But when you get HIV, you will not. If you think about it closely, how can you interpret this phenomenon in the gene expression data? You can understand this way. It may or may not be right because I'm not a biologist, but at least help you to understand. If you get HIV, maybe the relationship between genes get destroyed. So you do not have, for example, for some genes, they monitor your body. Okay, once they find your, the cold virus, they will respond. Okay, tell some other guys, hey, you guys need to do the job, to kill the virus. But for the HIV disease, this relationship get cut. So even if this gene, it knows, you get cold, but because they have not a relationship with all other genes, the relationship get cut. So, the genes which should do the job is not notified when you do get the cold. So that's why people try to invent this kind of so-called gene co-expression or association analysis. Just look at the relationship, gene relationship change or not, instead of look at the gene expression itself. Okay, so there's still the same question, for each individual gene, you define its relationship with all others. There are different ways to define that, but once you define it, you can check if this particular quantity, this relationship change or not across two different conditions. So here are several examples I grabbed from the internet, which show you such scenario does exist. Some genes, they are, in normal people, they are correlated. But for the diseased, they are not, or negatively correlated. So you can take a look maybe later for your on the handouts. So the way to detect this kind of so-called differentially associated, differentially co-expressed genes is still the same as before. Remember now we focus on the relationship quantity instead of the mean, the sample mean. So still the same. We still need to worry about the multiple, testing problem with the type 1 error. Okay, so that's what I have for the differential association analysis. The next one is the discriminant analysis. Home also mentioned this. What does discriminant analysis mean? Once you get your final differentially expressed gene list, like 30 genes, differentially expressed. So what you can do with these results? Of course, you identify some genes which may be responsible for the disease, but you can do more. This is one example. If you get your data and identify your differentially expressed genes, you can use these results to predict later on. For example, I can use this 8,000 genes data to train a model, and later on, if I get a new patient, I don't know if this patient is diseased or not, or which group it belongs to. And I can simply use my training model, plug in. I can predict which group it belongs to. So this is a reason. I know it's not very fun to read all this. Yes, sure, no problem.
This supervised machine learning,
yes.
Is it similar to a support vector machine? Like the logic behind calculating?
Support vector is one, another. It belongs to this. Okay. Yeah. Supervised. What does supervised mean? Supervised means you know in advance what group they belong to, the sample. Unsupervised, like later on the clustering analysis, you don't know which group. You just let the data tell. Okay. So you will see that later.
So almost same. It's something similar.
it's different method, but they do pretty much similar thing. Okay.
Because we have used in our analysis of
Oh yeah.
chemistry for predicting all candidate genes in primary immunodeficiency.
Okay, yeah, that's a very popular one. You will see that on my later slides. Okay, here's one most popular one is so-called linear discriminant analysis. What does it mean? Think about you have for one gene, for example. For the normal, you have some distributions on the left. If the people get diseased, they have another distribution. So the point is, we hope to get a cutoff in between, so that later on, if I get a new patient, I can tell, if it's less than that, I can predict it's normal. If it's greater than that, it's abnormal. So the whole point of the linear discriminant analysis is try to get the cutoff. So here it's only one-dimensional, so the cutoff is only only a point. But later on, you will see when you introduce the multivariate, more genes, basically this is going to become the hyperplane or the straight line. The linear. That's the point. Okay, here's I just picked two top differentially expressed genes. Do the scatter plot on the two-dimensional plane. The x-axis is one gene. The y-axis is another gene. Okay, I do the scatter plot, and I label them by two different colors. The point of the linear discriminant analysis is try to get a straight line in between, so that you cut there. If it's on this side, you claim belongs to this group. If it's on the other side, it belongs to the other group. So as you can see on the table, there are 37 genes, BCR, and 42 NEG. On the diagonal, that means they predict correctly. On the anti-diagonal 8 and 3, they have some misclassification. Of course, you do have some. There's always no perfect way to do that, but you can see the performance is quite good. The reason is,
how do you decide the cutoff between these two groups?
Roughly speaking, it's just the average of the two group mean. You can take the mean of one group, take the mean of the other group, you take the average. The average tells you but the shape of the line is determined by, it's more complex, procedure. It's not like they take the average. It's more like I'm not sure if I'm familiar with the linear regression stuff. You have to determine the coefficient so that determine the shape, the direction of this line. But as a epidemiologist, maybe you guys don't have to really understand what's going on underneath. But the point is here, it's better, to at least remember there is some tools available here to help you to get the cutoff.
Okay. So we need not worry about that.
Pardon me?
We need not worry about that.
If you want to go to the statistics department, you will. Yeah. Okay. Because I don't want to get that much details, because I have a lot. Later on, if you are interested, I will show you. Maybe. Okay. So another way to do this discriminant is a logistic regression. Logistic regression is people try to use different genes to predict the probability. Probability, the sample belongs to which group. So it's a little bit different way, but it's still gonna, I didn't print the results for the logistic regression, but I'm pretty sure it's going to give you similar cutoff here. But underneath, the statistically speaking, they're a little bit different. Okay, here I just list some other ways to do the discriminant. Before I talk about linear, here is a nonlinear alternative. Say support, your favorite one. It's right here. For the first one, quadratic discriminant analysis, quadratic means, compared to linear, quadratic means we use a quadratic curve to do the, to differentiate two groups. For example, here you see a straight line for the linear discriminant, but for the quadratic, you will see a quadratic curve. I'm not sure if you guys, have taken any calculus class, like for the Taylor expansion. People use the first, order term, most of the time, but sometimes they need a second order term. The quadratic, it corresponding to the second order term. They use more information, but it's more complex. It's not as simple as a linear discriminant, but it's going to provide better classification because, you use the variance terms inside. Okay, for the support vector machine, basically the idea is try to find a plane still between, so that this plane has a minimum distance from both groups. So anyway, so the k nearest neighbor, methods means you determine you do your prediction based on the neighbors. First you define for each sample or the distance between this sample to other samples. Once you get this distance, you can define your neighborhood, right? Which one is closer to which. So for each particular gene or particular sample, look at its neighborhood, maybe six neighbors, for example, six neighbors. If all six neighbors belongs to one group, you should predict your particular sample belongs to that group. This is the idea of the k nearest neighbor methods. But I don't have time I cannot show you each individual one, but the idea, pretty much similar, you will get this classification. Similar. Okay, that's for discriminant analysis. This is a principal, component analysis. The idea of the principal component analysis is, as I said, genes are highly correlated to each other. Think about it, essentially you only have one gene, and then you duplicate your genes 100 times. And at the end, it seems like you have 100 genes, but in fact, you only have one, right? You only have one. So that means the true dimension, even if I have 8,000 genes, but the true dimension, because they are highly correlated to each other, the true dimension may be much less than 8,000. So maybe it's around, according to my experience, most of the data, they have the true dimension around 10. Even use 10 combination, 10 principal components, they can explain most of the information in your data. So the point is, genes are correlated to each other. So some genes, maybe they are just duplicate, or some linear combination of others. So they're not that useful. So it's not very fun to read this. Let's go to, okay, so still the two genes in the previous slides. I plot them on this plane. And the principal component means this direction. You can see most points, they concentrate on this direction. So this is the longer arrow means the first component. That means, all the data concentrate on this direction. As you can see, the second, perpendicular to the first one is much shorter. The reason is that the information there is smaller. You have less information there. This is only two genes. You can imagine if you pull 8,000 genes together, you can do the same thing. At the end, you will have a principal component to certain direction. So they are the combination of the genes, but it gives you most of the information. So I understand this is the only two-dimensional, but you can imagine, to three-dimensional, four-dimensional, you have, all your data concentrate onto certain subspace of your, full space. Okay. Okay, cluster analysis. This is unsupervised learning. That means you do not know. For example, we forget about which group each individual sample belong to. Forget about that. We do not have that information. Can we still cluster, our samples to get, to recover the group information? The answer is yes. There is some ways to do that, the cluster analysis. So this is standard steps to do that. The point is, there are different choices or different methods, of the clustering. One classical one is a k-mean cluster. K-mean means you assume there are two clusters for your data, and then you try to use your software to fit, to see how these two clusters show in your data. So here I change the label, I change the x and y axis a bit. I just try to use the principal component, which I identified, in this analysis, and then also do the scatter plot of all the samples. And then if I use this k-mean clustering, it's going to cluster, our samples into two groups. So there are, as you know, there are many, biological meaningful groups like pathways, chromosome. this clustering analysis, help you to try to group either different samples or different genes together. So that if you throw in, like 10,000 genes, you will have a couple of groups. Okay, maybe these groups, all the genes, they behave similarly. They have some similar biological function. This kind of tool helps, biologists to identify the gene sets. So that, inside this set, genes have pretty much similar property. And also you can apply this clustering to the samples to cluster different samples, maybe normal, abnormal, or different normal.
Excuse me,
Yes?
I have one question.
Sure.
Looking at a very naive question.
Uh-huh.
While grouping, there are sometimes, say for example, with the pathway analysis, doing a gene expression data on that.
What analysis?
The pathway network analysis,
Uh-huh.
where grouping,
Oh, pattern,
so
okay.
There may not be the significantly non-redundant set.
Mm-hmm.
So there are sometimes the genes which are common to other groups.
Mm-hmm.
Will it be okay to include a non-redundant set?
I'm not sure what you mean by non-redundancy.
See, you said you can group it.
Yeah, I can group them.
Grouping. So in the grouping,
Yes.
so suppose if you are grouping it, there are sometimes based on certain parameters.
Yes.
Say for example,
Yes.
Cellular processes or biological processes,
Uh-huh.
in which sometimes the two genes might have a role in two different processes. So in that case, the genes which are in group A will be there in the group B too.
That actually the answer for this question, I believe, is what is your fundamental unit of your grouping? For example, you can define some prob set underneath your genes, or as you say, maybe some gene belongs to multiple groups. So your unit might not be genes, might be one level below.
It's a gene. Genes.
Well, the genes, you have like exon, there are different, subunits. Maybe they do belong to two groups. Sometimes it happens. Yeah.
Stupid question.
Yeah. Okay. Anyway, yeah, there are many like the hierarchical clustering, model-based clustering. There are many. The point is, I just want to show you guys, there are this kind of methodology available. Every time when you try to do the clustering, come here, you will always find some tools to get your job done. Okay, the very last one today I'm going to talk about, I know you're tired. The very last one is the so-called gene set enrichment analysis. It's invented by the people from MIT. The idea is, before in the differential gene expression analysis, we focus on genes. We try to test the genes if each individual gene are different across different conditions. But here people, say we already know, these genes should be grouped together. So we are more interested in if this group show difference across two different conditions, normal or abnormal. So we are more focused on the gene groups instead of individual genes. So if that's the case, there are two ways to do that. One way is for each individual gene, of course, you have a Ttest, for example, T-statistic. You can summarize, within each group, you can summarize the statistic for all the genes together to get a statistic for your whole gene set. And then you just compare this statistic across two different groups to get a significance. So you will eventually get a p-value for example, for the 8,000 genes here we have, maybe underneath there are essentially 80 groups. In each group we have 100 genes, for example. So at the end of this analysis, we will have 80 p-values, each corresponding to each gene set. So you can imagine this method reduces the dimensionality, significantly. So remember the Bonferroni procedure? You have to multiply 8,000, but here you only need to multiply 80. So of course it's more powerful because you have some prior information for the genes. You know these genes should be grouped together. So you have more information. Of course, you should be expecting more powerful results. Okay, another way to do that is you still focus on your individual, differentially expressed genes. Once you get your gene list, we have some tests available like the hypergeometric or Fisher exact test to say if two groups, they have overlap. You have your differentially expressed gene set, and you have different pathways. And you try to do the overlap for each known biological, gene sets. If they are overlap well, of course, you can claim, this gene set, they are different across two different conditions. Okay, this is gene set enrichment. And other methods, like including the network reconstruction, the Bayesian Boolean network, they try to get the dynamic of the genes, model which gene are the node, the edge connecting, node as a relationship. There are different ways to define that. But you can imagine it's a graph-based method, so that you can get a dynamic of all the genes. The other one is a ODE, ordinary differential equation. So I believe Hu, they have pretty good research on this. How to use the ordinary differential equation to analyze the gene expression data once you have the time course data. How the genes gene expression change when time goes by. Yeah, I cannot talk about too much about this. So anyway, I think that's all I'm going to talk today. So let me know if you have any questions. Huh?
Questions.
No?
You said you can ask questions, then you started clapping. That was no question.
Which is too bad. Yeah, anyway, later on, if you have some more questions, want to discuss with me, you can simply email me. My email is simply my name, RUI_HU @urmc.com. .edu. So